Hello students, till now we have discussed about divergence theorem and vector basics and coordinate systems, right? So from this class let us solve few problems on divergence and Gauss law by applying the learnt knowledge about vector basics. Okay, so let me read the first problem statement. Evaluate both sides of Gauss divergence theorem for the field D is equal to 2xyz into a cap x plus 3y square z into a cap y plus x a cap z coulomb per meter square. The region is defined by -1 to +1 meter for all the three axes x, y, z. This is the problem statement given. They are asking us to evaluate both sides of divergence theorem. Both sides of divergence theorem, right? For x, y, z means which coordinate system? This is rectangular coordinate system or Cartesian coordinate system for the length given by -1 to +1. -1 to +1 means it is a cubical structure for x, y, z for rectangular coordinate system. So let us write the equation for Gauss divergence theorem. What it says: surface integral of d dot ds is equal to volume integral of del dot d into dv. This is what we need to evaluate for both sides of this Gauss divergence theorem. That is what they are asking us to do. Now, in order to evaluate LHS part, in order to evaluate left hand side of this theorem, we need to know the differential surface of all the faces of the cube. So how do you evaluate differential surface area? In order to evaluate differential surface area of a cube using rectangular coordinate system, we need to go for Cartesian coordinate system representation. So let me write the Cartesian coordinate system representation of a cube. Okay. This is the cube which we have considered. This is x axis, this is y axis, and this is z axis. Okay, this is the cubical shape we have considered. So along x axis the length is -1 to 1, along y axis -1 to +1, along z axis -1 to +1. Here z is equal to 1, here z is equal to -1, here y is equal to 1, here y is equal to -1. At this point what we are going to get for this face? For this face x is equal to 1, at this point x is equal to -1. This is what they have mentioned here, from -1 to +1 for all the three axes. See, if we consider the height, this is from -1 to +1. If we consider the width, that is from -1 to +1 along y axis. If we consider the width, the length, then this is from -1 to +1 along x axis. That is what I have written here. So imagine this is a three-dimensional cube. Now in order to evaluate the differential surface area ds, we need to consider we need to consider how many faces? 6 faces of this cube. What are those 6 faces? Number 1, front face, back face, third one right, fourth left, fifth top, sixth one bottom. These are the 6 faces we need to consider. Now, if we consider 3 faces, top, front and side, then rest of the 3 faces are just opposite direction to those, right? If we evaluate 3 faces first, we can easily go for another 3 faces because it is just reverse of the direction of unit vector. Okay, so let me evaluate the differential surface area for differential surface area of front face. Okay, for front face we need to consider this one, this face. Okay, this face. Now let us choose a differential area in the front surface. This is ds. Okay, what is the length? What is this length? This length is, what is this length? This length is dy. What is this length? This length is dz. Okay, the unit vector coming out of this elementary surface is a cap x, which is equal to n cap. N cap is the unit vector coming out of this differential surface. The unit vector coming out of this overall front face is a cap x. Both are in the same direction, hence we can equate both the things. So for the front face, the differential surface area ds is equal to length into height, that is dy into dz into a cap x. This is the differential surface area for front face. So let us define this as ds front. Similarly, for back face, ds back is equal to dy into dz into minus ax. That's it, because the direction is opposite for the back face, then rest of the length are same. Hence ds back, differential surface area of the back face of the cube is equivalent to this one. Now similarly, if I consider the side face, this is front face, this is right. If I consider the right face, this one, front face is over, we need to consider the right face of this. For right face, which are the sides? The plane is xz plane. So along the xz plane, differential surface area for right face is equal to, what is this length? This length is dz. So let me write here. This length is dx and this length is dz. Okay, now this becomes dx into dz into, what is the unit vector coming out of this? This is a cap y into a cap y. Similarly, the differential surface area for left is dx dz into minus a cap y. Only direction is different. Similarly, if I try to evaluate for top face or top surface, this is how it is going to look. This is a cap z. The length and breadth are, this is dx, this is dy. Then ds top is equal to dx dy into a cap z. ds bottom is equal to dx dy into a cap minus a cap z. That's it. These are the 6 equations for calculating differential surface area of all the 6 faces of this cube. By using these 6 differential surface area, we can easily calculate the LHS part of Gauss divergence theorem. So what is D? D is given. D is 2xyz a cap x plus 3y square z a cap y plus x cap z coulomb per meter square. Now we need to take dot product between all the things. Now d dot ds for front face is equal to, what is that, 2xyz into a cap x plus 3y square z into a cap y plus x a cap z dot, since we are evaluating dot product, ds front. What is ds front? Ds front is equal to dy dz and a cap x, dy dz into a cap x. Now perform dot product operation. Therefore d dot ds for front surface is equal to how much? A cap x dot a cap x is equal to 1. Then rest of the things are perpendicular to each other. Then a cap y dot a cap x is equal to 0. A cap z dot a cap x is equal to 0. We left with only this quantity 2xyz into dy dz. A cap x dot a cap x becomes 1. So in order to obtain LHS part for the front face, we need to integrate this along with y and z plane. Therefore d dot ds is equal to integration of 2x y z dy into dz. If we integrate this, what is the limit? Minus 1 to plus 1. Y is equal to minus 1 to plus 1. Z is equal to minus 1 to plus 1. 2x is constant. Take it outside. This becomes what we are going to get? Integration of y z into dy into dz. What is the answer we are going to get? It is equal to 2x times of, this is y square by 2 from minus 1 to plus 1, z square by 2 from minus 1 to plus 1. What is the answer here? What is the answer we are going to get? 1 square 1 minus of minus 1 square. Minus 1 square is again 1. 1 minus 1 0. 0 into 0 0. So answer is 0. The total flux obtained from front surface is 0. That means the total flux obtained from back surface is also 0, obviously, because only the direction is reversed. So the total flux obtained from front and back surface is 0. Similarly, we need to evaluate the total flux obtained from top and side surfaces. Let us continue the problem for the side face. So d dot ds for right surface. Right surface is equal to, what is d? 2xyz a cap x plus 3y square z a cap y plus x a cap z into what we are going to get? We are going to get dx into dz into a cap y. This is ds for the right surface. For right surface, this is dx, dy and a cap y is the unit vector. Now a cap y dot a cap y becomes 1, then rest of the two unit vectors, dot product of rest of the two unit vectors becomes 0. Hence what we are going to get here, we are going to get 3y square z into dx into dz. Look at this, only this term is going to get. Now integrate with respect to what? Which quantities? 3y square into z, that is xz plane. With respect to x and z, we need to integrate this 3y square z dx into dz. What we are going to get? 3y square is common, 3y square is constant, take it outside. Integration from x is equal to -1 to +1, integration from z is equal to -1 to +1, z into dx into dz. So what is the result? 3y square into see, integration of -1 to +1 dx, integration of -1 to +1 z into dz. What we are going to get? 3y square into, see, 1 minus of -1, this is 2 into what we are going to get? Z square by 2. Z square by 2, the answer is 0. Then the total flux is 0. For the right surface, the total flux is 0. Similarly, for the left surface also, the total flux becomes 0. Now we need to evaluate for top and bottom surface. For top surface, d dot ds is equal to 2xyz a cap x plus 3y square z a cap y plus x a cap z into, which are the planes? What we are going to get? X and y plane, dx into dy into a cap z. We left with only this term because rest of the two are orthogonal to a cap z. So resultant is 0. D dot ds is equal to x dx and dy. Okay, x dx into dy. If we integrate this with respect to x and y plane, x dx into dy, what we are going to get? Integration of x is equal to -1 to +1, x into dx, integration of y is equal to -1 to +1 into dy. So the answer is x square by 2 from -1 to +1 into y from -1 to +1. The result is 0. For top and bottom surface also, the total flux is 0. Therefore surface integral of d dot ds is equal to 0 for entire 6 faces of the cube. Therefore LHS part of the Gauss divergence theorem is 0. Similarly, we need to evaluate RHS part. What is RHS part? RHS part is del dot d, volume integral of del dot d into dv is equal to this one. We need to evaluate this one. What is gradient dot d? Del dot d is equal to dou by dou x of dx plus dou by dou y of dy plus dou by dou z of dz. What is dx component? Dx component is 2xyz, dy is 3y square z, dz is x. Okay, then gradient dot D is equal to dou by dou x of 2xyz plus dou by dou z of dy. What is dy? 3y square z. 3y square into z plus dou by dou z of dy. What is dy? X. Okay. So what we are going to get? See, gradient dot D is equal to, with respect to x, if I do this, what we are going to get? 2yz plus, what is this? With respect to y, sorry, not z, with respect to y, this becomes 6yz plus, what is this? 0. Okay. So what is the answer? Del dot D is equal to 8yz. Del dot D is equal to 8yz. We need to integrate with respect to v. What is dv? dv is equal to dx into dy into dz. Differential volume. dv is equal to dx into dy into dz. Now in order to evaluate RHS part, triple integral of x, y, z with respect to volume, 8yz into dx, dy and dz. 8 is common, take it outside. Okay. Integration of dx, integration of y into dy into integration of z into dz. See, 8 times of from minus 1 to plus 1, from minus 1 to plus 1, from minus 1 to plus 1. See, what is the integration of dx? That is x from minus 1 to plus 1 into, what is this? So, y square by 2 from minus 1 to plus 1 into z square by 2 from minus 1 to plus 1. So if I try to evaluate this, apply the limits. So this quantity becomes 0 and this quantity becomes 0. This becomes 2. So 0 into anything, 0. Therefore RHS part is also equal to 0. Therefore the total flux provided by that cube within this given region is 0. Hence we evaluated the Gauss theorem for the given problem statement. Understood? Thank you. Let us discuss about potential difference and work done on a unit positive charge. So in order to, before going to these topics, let us understand a simple analogy. Okay. So consider a situation where strong breeze flowing from north to south direction. You need to move a rock opposite to that wind direction. So what you need to do? You need to push the rock in the opposite direction to the direction of the wind, right? So you need to perform some work in order to push that rock from one point to another point. So the direction of pushing is opposite to the direction of wind. That means you need to put some effort. So keep this analogy in your mind in order to define potential and potential difference of a particular point charge. Okay. Let me define what you mean by electrostatic potential of a point charge. Okay, in electromagnetic wave theory. So let me define in a formal way. Electric potential at a point in an electric field is the work done in bringing a unit positive charge from infinity to that point in opposite to the electric field. Have you understood? Let me write here. Electrostatic potential. Let me define this. The potential at a point in an electric field is the work done in bringing a unit positive charge from infinity to that point in opposite to the direction of field. This is called electrostatic potential. The electrostatic potential at a point in an electric field is the work done in bringing a unit positive charge from infinity to that point in opposite to the direction of field. So as I said earlier, so remember that analogy, you need to push the rock in opposite direction to the direction of the breeze. Okay, so you need to put certain amount of energy to that, you need to perform some work, so that work done is defined as a potential here. Okay, and one more concept, what do you mean by potential difference? So what do you mean by potential difference? See, in this particular definition, we are bringing a unit positive charge from infinity to a particular point in an electric field. Here, potential difference means you are bringing unit positive charge from one point to another point in a given electric field. So the 2 points are considered within the same electric field, but the direction of work done is opposite. The direction of pushing the unit positive charge in an electric field is opposite to the applied uniform electric field. Now let me define what do you mean by potential difference. Potential difference in an electric field, same as that. Potential difference at a point in an electric field is the amount of work done in bringing a unit positive charge from one point to another point in opposite to the direction of field. Same definition holds good. Instead of infinity, you are pushing a unit positive charge from one point to another point in opposite to the direction of electric field. Let me define here. The potential difference in an electric field is the amount of work done in bringing a unit positive charge from one point to another point in opposite to the direction of the field. Okay, so let me depict this potential difference here. So let us have a uniform electric field E. Let us have the uniform electric field E which is in this direction. Okay, understood? Now let us consider a unit positive charge at this point. Let us consider a unit positive charge which is Q at this point. Okay, you need to push this unit positive charge from A to B. Okay, the direction is opposite to the applied electric field. Okay, so the potential difference is defined as moving a unit positive charge from one point to another point in a given electric field in opposite to the direction of the given or applied electric field. The amount of work done is called as potential difference. That is what we are discussing here. Got it? Now, moving a unit positive charge from point A to B, the amount of work done in order to move a charge from A to B in a given electric field in opposite direction is called as potential difference. So, moving a unit positive charge from infinity to a particular point in an electric field is called as electrostatic potential. From infinity to a point in an electric field is called as electrostatic potential. From a point in an electric field to a point in the same electric field, it is called potential difference. We know that there are two potential differences within the given electric field. So we can assume it as a from lower electric field intensity to higher electric field intensity, lower potential to higher potential. We can call like that. Okay. Let us move on to the next topic. Energy expended in moving a point charge in an arbitrary direction in an electric field. So let us assume a uniform electric field. Okay. This is the electric field which is uniform in the space. Let us consider point A which is arbitrarily chosen. The charge at this point is Q. Okay. In the previous section, while defining potential difference, we have taken point B here, which is normal to this, normal to point A. Now, point B is chosen arbitrarily. Point B is chosen arbitrarily inside this electric field. Okay. Now, the length from A to B is delta L, a small length. Okay, arbitrary small length has been considered. The angle which forms the differential length delta L forms an angle with the direction of electric field, that is theta. Then opposite to this is 180 minus theta, right? This angle is 180 minus theta. We know that if we place a unit positive charge inside an electric field, it induces a force, it responds to some force, right? Okay, so it is affected by a force that is defined by Coulombs law, where F is equal to Q1 into Q2 divided by 4 pi epsilon naught into R square. This is the Coulombs law equation we have seen. Now, if the charge placed in these 2 points are unit positive charge, then this equation becomes Q into Q divided by 4 pi epsilon naught into R square. If one of the charge is unit positive charge, then this becomes E is equal to Q divided by 4 pi epsilon naught into R square. Therefore, I can say F is equal to Q times of E. Looking at the above equation, F is equal to Q times of E. This can be represented as E. Therefore, F is equal to Q times of E. If one of the charge is unit positive charge and another point is having the magnitude of Q, then F is equal to Q into E. Got it? So at point A, it experiences some force because it is placed inside the electric field intensity. Okay, keep that in our mind. Now F is equal to Q into E. Now what is the amount of work done in order to move a unit positive charge from A to B? What is the amount of work done? The amount of work done in order to move a charge from A to B is defined as the potential difference. Okay, amount of work done is equal to the potential difference, that is VB minus VA. In the previous case, in order to move a charge from one point to another point is called as work done, which is the potential at point A is VA, potential at point B is VB. In order to move a charge from A to B, you need to do some work. That work done is called as potential difference, that is VB minus VA. That is what we have written here. Okay. Now coming back to this, the component of force acting opposite to this electric field is this one. The component of force acting opposite to the applied electric field is this component. This can be represented as F times of cos of 180 minus theta. This component is F cos of 180 minus theta. Therefore, the force component acting opposite to the field is F cos of 180 minus theta. This can be written as minus F cos of theta. 180 minus theta is minus cos theta, right? This is this one. Now the amount of work done in bringing a charge from A to B, that is W is equal to minus F cos theta into delta L. The work done into the length which is travelled from one point to another point, this one. Therefore W can be represented as minus F is equal to Q into E cos theta into delta L. If we represent this in terms of dot product, W is equal to minus Q into E dot delta L. If we represent this term in terms of dot product, we know that dot product is equal to magnitude of one quantity into magnitude of another quantity into cos theta. See, these are the magnitudes of two quantities, E and delta L. If we represent in terms of dot product, these two becomes vectors. Therefore work done or potential difference is represented in this form for a arbitrary movement of charge inside the electric field. Got it? Moving on to the next part, line integral of the electric field and the potential difference. So what we have got in the previous discussion, W, that is work done, is equal to minus of Q into E dot delta L. What is this delta L? Small distance, small length, delta L. If this small length becomes very little, then as limit delta L tends to 0, delta L becomes dl, right? This is what we have used so many times. Then W becomes dW. Work done becomes differential work done, that is dW is equal to minus Q into E dot dl. This is another useful relationship you need to remember. Now coming to the line integral of the electric field and the potential difference. What is this means? Let us choose a uniform electric field again. Let us choose uniform electric field E. Okay. So let us consider a point, arbitrary points A and B. Let us choose arbitrary points A and B. The charge at this point is Q, unit positive charge, plus Q. Okay. The distance from A to B is divided into small segments. The distance from A to B is divided into small segments. Let us write it as delta L1, delta L2, delta L3, delta L4, delta L5 and so on. The distance from A to B is divided into small segments, delta L1, delta L2, so on. Okay. Now the corresponding electric field for each of the segment is defined as E1, E2, E3 and so on. Okay. Now let me write the equation for W. W is equal to minus Q times of E dot delta L, right? Now W can be rewritten in this form. See, for E1 this becomes delta L1 plus E2 dot delta L2 plus E3 dot delta L3 and so on up to infinite number of segments. We can take infinite number of segments. Got it? Like this. Now if we sum up all these quantities, then the equation results in minus Q times of summation of EI dot delta Li. Is it correct? If we sum up all these segments into a single equation, then summation comes into picture. Then summation of all these quantities EI dot delta I gives us the same set of equations. Now if I apply limit as delta L tends to 0, then delta L becomes dl. Okay, delta L becomes dl. The elements, as the segments becomes infinitely small, 0, the segment length is 0, then summation will be replaced by integration, because it becomes continuous. As the length of each of the segment tends to 0, then the distance becomes continuous. Therefore W is equal to minus Q times of integration from A to B EI dot dl, right? This is what we are going to get, E dot dl. In general, W is equal to minus Q times of A to B E dot dl. This is what the line integral. Okay. Now W can be represented as VB minus VA, work done or potential difference, is equal to minus Q times of integration from A to B E dot dl. Okay, another important equation. Then coming to the special case. Special case. What is that special case? When the electric field is uniform. Look at this diagram. for each and every segment electric field is taken as E1, E2, E3 and so on, right? Now the electric field is constant throughout the segment, therefore E is a constant term. Let us take E outside this integration, therefore minus Q into E times of integration dot integration from A to B dl. Okay, if we integrate this differential length, what we are going to get? E dot L from A to B. Okay, then W is equal to minus Q times of E dot L from A to B. This is what we are going to get. Simply we can easily substitute this equation in order to calculate the work done or potential difference when the electric field is uniform. Okay, thank you.